Today's lesson is on the fundamental counting principle. We're going to determine the number of outcomes in an event or an experiment. So let's look how the fundamental counting principle works. The first thing you need to do is figure out the total number of outcomes. So let's look at that with using license plates. So in this example, license plates are being produced that have a single letter followed by 3 digits. All license plates are equally likely. We're going to find the number of possible license plates using the fundamental counting principle. So the first thing you need to do to find the total number of possible license plates, meaning all outcomes, is determine the number of items that you have. So again, it was a letter followed by 3 digits. There are 26 possible choices for a letter, 10 possible choices for a digit because you have the digits 0 through 9. Again, the third item is a digit, and the fourth item is a digit. You multiply those values together to determine the total number of outcomes. 26 times 10 times 10 times 10 is 26,000. So there are 26,000 total number of possible license plates using a letter first and then 3 digits. To find out the probability of a specific license plate, you need to use the total number of outcomes in the denominator. Then you can determine how the probability is based on the question. So we're finding the probability that a license plate has the letter Q. So probability of Q. These 3 blank spots represent the digits, but all digits are possible. So there's only one Q in the alphabet, but we can use any of the digits. So 1 times 10 times 10 times 10 is really 1,000 over 26,000. You can simplify that to 1 over 26, and as a decimal, it's approximately 38 thousandths. If I wanted to make that into a percentage, it's approximately 3.8%. So what is the probability that a license plate does not contain a specific number? First, we use the fundamental counting principle to find the number of license plates in total, and then the license plates that do not contain a 3. We already know that based on our prior example, there are 26,000 possible license plates. But if we want the probability of not a 3, we would have 26 possible letters, but only 9 possible digits in every other scenario, all over 26,000. This would equal 18,954 over 26,000. If I want to divide that to get the decimal version, it's approximately 729 thousandths or 72.9% chance of not containing a 3. So let's look at something that you're more familiar with, Social Security numbers. All Social Security numbers contain 9 digits, and all Social Security numbers are equally likely. First, we'll find out the total number of possible Social Security numbers. Each digit, meaning the first possible digit in your Social Security number, has 10 possible choices from 0 to 9. So each one of these has the possibility of 10 values that can be used in a Social Security number. So 10 times 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 10, which equals 1 billion possible choices. Now, to find the probability that a Social Security number contains the number 7, it means that it has to have at least one number 7, the probability of a 7. The 7 could be anywhere in the value. I don't need to make sure that each one of those has a 7, just one does. So out of the 1 billion, one of them has to contain a 7. Let's pretend it's the first one that got the 7. That means all of the other choices are equally likely, any digit between 0 and 9. When I simplify it, I get the value 1 over 10, or 10%. The fundamental counting principle tells you only the number of outcomes in some experiments, not what the outcomes are. A tree diagram is a way to show all of the possible outcomes. For example, a baker can make a yellow or white cake with a choice of chocolate, strawberry, or vanilla icing. When we want to describe all of the combinations of cakes, we need to make a tree diagram. Follow along as I make the diagram for you. You'll notice that there are 6 possible combinations of cake: yellow cake with chocolate, vanilla, or strawberry icing, or white cake with chocolate, vanilla, or strawberry icing. Together, we look at that final row, meaning there are 6 possible combinations of cakes. But the types of cakes that we would describe are based on the tree diagram. So we're going to use a tree diagram for this dependent event. Then we're going to use what we know about compound events to try and determine mathematically. There are 7 black socks and 2 white socks in a drawer. 2 socks are removed. What is the probability that the colors matched? Meaning I get 2 black socks or 2 white socks. So first, we're going to draw a tree diagram. Follow along with my diagram and put that in your notebook. Notice that drawing this as a tree diagram takes quite a bit of time as there are so many options. If we're trying to do it with a tree diagram, we would have to continue to go down through 9 different layers to do this dependent event. Rather than doing that, we can use what we know about dependent events. So for black socks, and we have white socks, there are 7 black socks and 2 white socks. The probability of getting 2 black socks or the probability of getting 2 white socks. So the first probability of getting a black sock would be 7 out of 9. And then the second possibility would be 6 out of 8. We know that we multiply these values together and we get 42 out of 72. I'm not going to simplify that yet because I'm going to need to combine it with the possibility of getting 2 white socks. If I wanted a white sock on my first pick, I would have 2 out of 9. If I wanted the second one to be a white sock, I only had the option of 1 out of 8, which gives me a total of 2 out of 72. But if I want either the probability of getting 2 black socks or 2 white socks, I need to add these 2 values together at the end, getting 44 over 72, and I can simplify that value to 11 over 18. If I wanted to make that into a percentage, I would take 11 divided by 18 to get approximately 0.61, which would be 61% chance of getting a match. Notice that the denominator here was 72. When I was done with all of my rows, I would have 72 possible outcomes.